So, welcome to the lecture series on mathematical methods and applications. In the last few lectures, we have seen that what Laplace transforms are, what are their properties, and how can we solve an ordinary differential equation or a partial differential equation or integral equations using Laplace transforms. Now, the next topic is Fourier series. Now, in this lectures, we will see that what Fourier series are and what is the convergence theorem for Fourier series and what are the applications of Fourier series or Fourier integrals. Okay. Now, first introduction on Fourier series. It is named after a French mathematician and a physicist, Jacques Fourier, who was the first to use Fourier series in his work. A series expansion of a function in terms of a trigonometric functions cos mx and sin nx is called a Fourier series. So, Fourier series is nothing but if we express a function in terms of sine and cosines, then we call such a series as Fourier series. Many functions including some discontinuous periodic functions can be written in the Fourier series, and hence it has a wide application in solving ordinary and partial differential equations. Now, let us start with this set. Set is 1 cos pi x by L, cos 2 pi x by L and so on, sin pi x by L, sin 2 pi x by L and so on. Now, what is an orthogonal set of functions? How we define it? Suppose we have some functions, suppose functions are f1, f2, f3 and so on, and it is defined suppose defined in a comma b. Then we say that this set of function is orthogonal if in this interval if integral a to b f I x into f j x dx is equals to 0 for all I not equal to j. So, if this condition hold for set of functions f1, f2 up to f3 and so on, which is defined in the interval a comma b, then we say that this set of functions are orthogonal. Okay. Now, consider this set 1 cos pi x by L, cos 2 pi x by L and so on, sin pi x by L, sin 2 pi x by L and so on. Now, in the interval minus L to L, if we see if we carefully see, then minus integral minus L to L cos m pi x by L dx and this equal to 0. Again the second inequality holds, the second inequality also hold, it is 0 when m not equal to n. The next inequality minus L to L sin pi m pi x by L and sin n pi x by L dx equal to 0 when m not equal to n and L when m equal to n. So, this we can derive very easily, and minus L to L cos pi m pi x by L into this is also 0 for all m and n. So, hence if you take any two multiples in this set, if you take any two different functions and integrate from minus L to L, it is always 0. So, we say that this set is an orthogonal set of functions, okay, because it satisfies this condition, because integral a to b f I x f j x is 0 for all I not equal to j, and this set satisfies this property. Hence, we say that this set is nothing but an orthogonal set of functions. Now, let f x be a periodic function of period 2L and defined on an interval minus L to L. Okay. Assume that now we are assuming that it can be expressed as a linear combination of trigonometric functions of cos mx and sin nx. So, what I want to say? So, first I construct a orthogonal set of functions, and that set is nothing but this set 1 cos pi x by L, cos 2 pi x by L and so on, sin pi x by L, sin 2 pi x by L and so on. Okay. This is an orthogonal set of function, and a function which is periodic, okay, in the interval minus L having a period 2L defined on minus L to L, which is given, can be expressed as a linear combination of these functions, that is some multiple of this we are taking for convenience as a naught by 2 plus a1 into this, a2 into this and so on, b1 into this, b2 into this and so on. So, which can be written as summation n from 1 to infinity a n cos n pi x by L plus summation n from 1 to infinity b n sin n pi x by L. Okay. This function we can write as a linear combination of these trigonometric functions sin and cos. Now, if you want to find out the values of a naught, a n, b n and so on. So, how can you find these values? So, what the expression is basically, this is a naught by 2 plus a1 cos pi x by L plus a2 cos 2 pi x by L and so on plus a n cos n pi x by L and so on. This is what we are having here, and here it is b1 sin pi x by L plus b2 sin pi x sin 2 pi x by L sin 2 pi x by L and so on plus bn sin n pi x by L and so on. So, basically the linear combination of these functions is this thing or this thing. Okay. Now, to find out the value of a naught, let us integrate both the sides from minus L to plus L. Okay. So, if we integrate from minus L to L, in this side is minus L to L fx dx is equals to a naught by 2 integral minus L to plus L dx plus, now integral minus L to L cos n pi x by L for every n is 0 and integral minus L to L sin n pi x by L dx is 0 for any n. So, that means these all are 0. So, this implies a naught is nothing but 1 by L times minus L to L fx dx. So, that is how we can compute a naught, my 1 by L minus integral minus L to L fx dx. Okay. Now, suppose we want to compute a n may be 1, 2, 3 and so on. Suppose you want to compute this a n. Okay. So, you multiply both sides by cos n pi x by L. Okay. So, when you multiply both sides by cos pi x by L, it is fx into cos n pi x by L integrate from minus L to plus L dx is equal to, now here if you multiply and integrate from minus L to L, cos pi x by L is 0 for any n. Now, if it will be not 0, cos into cos is not equal to 0 only when m equal to n, that is n equal to n, and in all other cases it will be 0, and cos and sin multiple is always 0 for any m and n, this is always 0. Here what we have, here it is nothing but a n integral minus L to L cos square n pi x by L into dx, and we have already seen that this value is nothing but L, a n into L, because when m equal to n, so this value is nothing but L, this we have already seen. So, from here we can say that a n is nothing but 1 by L times integral minus L to L fx cos n pi x by L into dx. So, this is how we can find out a n. And what is n? N may be 1, maybe 2, maybe 3 and so on. Okay, clear? Now, suppose you want to find out Bn. In the same way, you multiply both the sides by sin n pi x by L, that is integral minus L to L fx into sine n pi x by L into dx. You integrate both the sides. Here integral minus L to L sine n pi x by L is 0, and the multiple of sine n cos for any m and n integral minus L to L is always 0. So, all these terms are 0, and here we have here when m is not equal to n it is 0, we left with only bn. So, integral minus L to L bn into sine square n pi x by L into dx, and this value is nothing but L when m equal to n, so it is bn into L. So, this implies bn is nothing but 1 by L integral minus L to L fx sine n pi x by L into dx. So, these formulas are called basically Euler's formula, okay, to find a naught, a n and b n. So, if we assume that if we express function periodic function f x as a linear combination of cos trigonometric functions of cos and sine, then a naught, a n and b n can be found using these expressions, okay. Now, let us solve some problems based on this, that how we can find a Fourier series of a periodic function. So, basically if we have a periodic function f x of period 2L defined in minus L to L. So, what will be f x? What we have learned, that f x is nothing but a naught by 2 plus summation n varying from 1 to infinity a n cos n pi x by L plus summation n from 1 to infinity bn sine n pi x by L. Now, what is a naught? A naught is nothing but 1 by L integral minus L to L f x dx. This we have derived. A n is nothing but 1 by L integral minus L to L f x cos n pi x by L into dx, and what is bn is 1 by L integral minus L to L f x sine n pi x by L into dx. Here in these two expressions n is 1, 2, 3 and so on. So, now let us solve this problem. Here it is given that function is periodic and has a period 2L, oh so sorry 2 pi, okay. And what is function? What is the nature of the function? Function is pi plus x when x is varying from 0 to pi, 0 to minus pi, and it is 0 when 0 less than equals to x less than pi, and f x plus 2 pi is f pi f x, because period is 2 pi. So, what is the shape of the function? When it is minus pi, so it is 0, and when it is 0 it is pi. So, here it is like this, and from 0 to pi, suppose pi is here, from 0 to pi it is 0. Again from pi to 2 pi it is this function, say having the same height, and from pi to 3 pi is again 0. Then 3 pi to 4 pi again it is this line, and 4 pi to 5 pi it is 0. So, this function is something like this is the shape of this, I mean graph of this function. Now, how can we find the Fourier series of this function? So, we will express this function in this form, a naught by 2 plus summation a n cos n pi x by L plus b n plus summation b n sin n pi x by L. Now, we first compute a naught and a n b n. What is a naught? A naught is nothing but 1 by L. Now, instead of L, here we have pi, because 2L is 2 pi, so that means L equal to pi. So, it is 1 by pi integral minus pi to plus pi f x dx. So, this is nothing but 1 by pi integral from minus pi to 0 it is pi plus x, otherwise it is 0. So, it is nothing but 1 by pi, and this term is nothing but pi x plus x square upon 2 minus pi to 0, upper limit minus lower limit. When you apply the lower limit, it is nothing but negative of pi into minus pi plus pi square upon 2, and it is minus pi square by 2, that is pi by 2. So, this is A naught. Okay. So, A naught for this problem is pi by 2. So, I am writing here A naught is nothing but pi by 2 for this problem. Okay. So, A naught is pi by 2. Now, let us find An. An is nothing but 1 by pi integral minus pi to plus pi fx, and it is cos n pi x by L, L is pi into dx. So, pi cancel out, it is nothing but 1 by pi integral minus pi to 0 pi plus x cos nx dx, which is nothing but 1 by pi. Now, you will integrate this, applying integration by parts. So, it is first as it is integration of second sin nx upon n minus this derivative is 1 into integration of this, that is minus cos nx upon n square from minus pi to 0. So, this is nothing but 1 by pi. When x equal to 0, sin is 0, and when x equal to pi or minus pi, sin n pi is 0. So, this term is 0 from the lower limit and the upper limit. So, this term is 0. When x is 0, cos 0 is 1, and when x is minus pi, it is cos n pi, and cos n pi is minus 1 for negative n, for odd n. I mean, what is cos n pi? Cos n pi is nothing but minus 1 ki power n. When n is odd, it is minus 1, and when n is even, it is 1. So, this is nothing but minus plus, it is 1 by n square minus cos n pi by n square. So, this is nothing but 1 by pi n square 1 minus 1 ki power n. So, this is An for this problem. So, what is An? An will be nothing but 1 by n square pi 1 minus 1 ki power n. Now, let us compute the last term, that is Bn. Bn will be nothing but again 1 by pi integral minus pi to pi. It is fx sin n pi x by L, L is pi. So, this is 1 by pi, again integral minus pi to 0, it is pi plus x by the definition of the function. Now, again you will integrate by parts here, pi plus x sin nx, okay, integration of this. So, integration of this is nothing but minus cos nx by n minus derivative of first, integration of second, that is minus sin nx by n square from minus pi to 0. Now, again this term, when you take x equal to 0, it is 0, when you take x equal to minus pi, it is 0, and here you can take minus outside 1 by pi. When you substitute x as minus pi, it is 0. When you take x equal to 0, it is pi by n. Okay. When you take x equal to 0, it is pi by n, and when you take x equal to minus pi, it is 0. So, it is nothing but minus 1 by n. Okay. So, what will be, so Bn is nothing but minus 1 by n. So, what will be the Fourier series of this function? So, Fourier series representation of this function fx is nothing but, so fx can be written as a naught by 2. What is a naught? A naught is pi by 2. A naught by 2, that is pi by 4. pi by 4 plus summation n from 1 to infinity an. An is nothing but this expression. So, it is 1 by n square pi 1 minus 1 ki power n into cos n pi x by L plus summation n from 1 to infinity, it is Bn sin n pi x by L. What is Bn? Minus 1 by n. It is minus 1 by n sin n pi x by L. So, which if we expand this, it is nothing but pi by 4 plus when n is minus, when n is 1, it is nothing but 0, and when n is 2, okay, when n is 1, it is nothing but 2. For even values of n, it is 0. So, that means from here only odd values come. It is nothing but 2 will be outside, 2 upon pi, and it is nothing but and this L is nothing but pi, sorry, this L is nothing but pi. So, pi cancels out because L is nothing but pi. So, you substitute when you substitute x as 1, so when you substitute x as 1, so it is 2, so 2 I am taking outside, pi I am taking outside. So, it is cos x upon 1 square plus cos 3 square and so on, and minus it is sin x upon 1 plus sin 2x upon 2 plus sin 3x upon 3. So, this will be the Fourier series representation of this function f x. Okay. Now, let us solve one more problem based on this Fourier series representation of this function and hence deduce this series. Okay. So, let us solve this problem also. So, here period is again 2 pi. So, L equal to pi, okay, and function is x minus x square. So, we directly compute a naught, a n and b n. After calculating a naught, a n and b n, we substitute it over here, find f x, and hence the Fourier series representation of this function, and then substituting some values of x, we will try to obtain this series. Okay. So, what is f x here? F x is x minus x square. Now, what will be a naught? Again 1 by pi minus pi to plus pi f x dx. It is 1 by pi minus pi to plus pi x minus x square by 2 dx. Now, this x is an odd function, from minus pi to pi it is 0, and this x square is an even function, so it will be 2 times. So, we can easily write it is minus 2 by upon pi 0 to pi x square dx, okay, and it is nothing but minus 2 upon pi, it is x cube upon 3 0 to pi. So, which is nothing but minus 2 upon pi cube by 3, and it is equal to minus 2 by 3 pi square. So, this is a naught for this problem, So, I am writing a naught over here, a naught is minus 2 by 3 pi square. Now, let us compute a n for this function. So, what will be a n? A n is 1 by pi integral minus pi to plus pi f x cos n pi x by L into dx. Okay. Now, again x into this is odd function, it will be 0 from minus pi to plus pi, and x square into this is an even function, so it will be 2 times. So, we can write it here minus 2 upon pi integral 0 to pi x square cos n x dx. So, this is nothing but minus 2 upon pi, you will integrate by parts, x square sin nx upon n minus 2x, this is minus cos nx upon n square, then plus 2 this is minus sine nx upon n cube, and the whole expression from 0 to pi. Now, whatever terms of sine from 0 to pi is 0, because upper limit is 0, sine n pi is 0 and sine 0 is 0. So, this is 0, this is 0. Now, only this term left. Now, it is also when x is 0 is 0. So, only the above limit left. It is minus 2 upon pi, it is 2 pi, and it is cos n pi upon n square, which is nothing but pi cancel out. So, it is minus 4 by n square into minus 1 ki power n. So, a n is nothing but minus 4 upon n square minus 1 ki power n when n varying from 1, 2, 3 and so on. Okay. Now, Bn can be calculated in the similar way. So, what will be Bn? Bn will be 1 by pi integral minus pi to plus pi x minus x square sine n pi x by L into dx. Now, x into this is an even function and this is an odd function. This will be 0 and we left with only 2 upon pi integral 0 to pi x sine n x dx. Now, again integration by parts, it is first as it is, integral of second it is minus cos n x upon n minus 1 into integral of this, that is minus sine n x upon n square from 0 to pi. Now, this will be 0 when x is pi and when x is 0, only this will be left. So, it is minus 2 upon pi n, I am taking outside. So, it is only exists when x is pi. So, it is pi into minus 1 ki power n. Okay. Pi cancel out. Bn is nothing but minus 2 by n into minus 1 ki power n. Okay. Now, so what is the Fourier series representation of this function? What is the function x minus x square? So, fx will be equal to a naught by 2, a naught is this term. So, a naught by 2 is minus pi square upon 3 plus summation n from 1 to infinity an is minus 4 by n square minus 1 ki power n cos nx plus summation n from 1 to infinity bn is minus 2 ki power 2 upon n minus 1 ki power n sin nx. So, what this series is? This is minus pi square upon 3 minus 4 times. When you take n equal to 1, when n is 1, it is minus cos x. When n is 2, it is plus cos 2x upon 2 square. When n is 3, it is minus cos 3x upon 3 square and so on. And it is minus 2 times. When n is 1, it is minus sin x upon 1 plus. When n is 2, it is sin 2x upon 2. When n is 3, it is minus sin 3x upon 3 and so on. Okay. So, now we want to formulate this series. Okay. This is the Fourier representation of this function. Okay. The first part is over. Now, we want to deduce this equal to pi square by 12. Now, it is 1 by 1 square, 1 by 2 square with alternate signs. Okay. 1 by 3 square, 1 by 4 square with alternate sign, and we do not want any term from this series. So, this we can obtain putting x equal to 0. When we put x equal to 0, all these terms are cos x, cos 2x, cos 3x, all will be 1 and all this will be 0. So, put x equal to 0. So, when you put x equal to 0, the left hand side is 0, it is minus pi square by 3, take minus common from here, it is 4 times, it is 1 by 1 square minus 1 by 2 square plus 1 by 3 square and so on, and this is 0. So, what will be the series of this? It is nothing but 1 upon 1 square minus 1 by 2 square plus 1 by 3 square and so on is equal to pi square by 3 will go here, divide by 4, so it is pi square by 2. So, hence this result can be obtained. Okay. So, in the next class we will see that how we can say that what is the convergence theorem for the Fourier series, that we will see. Okay. So, thank you very much.